So I start by making a picture for U, and let's say this is V, and this is the angle theta. And then we have learned that when you do U cross V, or actually V cross U, it doesn't matter, and you calculate the length, it's the length of U times the length of V times sine of theta. So now the point is the length of U, okay, we see here, but what is actually V times sine of theta? So what is this actually? Can we see this one in the picture? And I should also make absolute value here, just in case. Although in my picture, I don't need it. It turns out when you think about the unit circle, the sine is always the y-axis. So it turns out norm V times sine theta is actually this guy here. If here's a perpendicular, so this here is actually norm V times sine of theta. So now you can say, oh, but then we have base times height. That's what this is. So it turns out U cross V, the norm, the length of this vector, which we now know how to calculate, is actually equal to the area of a rectangle. And it's this rectangle. It's base times height. Okay, that's a result, but it turns out, and I think you have done this essentially the opposite way in high school, when you actually found out the formula for parallelogram. Now you can say, yeah, but this one here, we can also add here. So it turns out the area of the rectangle is equal to the area of the green parallelogram. So it turns out the norm of the cross product, when you calculate the cross product and then you calculate the length, is equal to the area of the parallelogram given by U and V. Okay, and now I hope I don't overburden this picture here. You can also split the parallelogram in half. Okay, now it's not good with my colors. So it turns out, okay, maybe I make a new picture. So we have U, I try to make the same V, and we just had this parallelogram. So this is another U, V. But if you cut it like this, you get this triangle twice, once here, and that's a triangle with sides U and V. So it turns out U cross V is 2 times the area of the triangle given by U and V. Okay, so this is some geometrical insight. So if you calculate, and I should make this nicer, so this is U cross V. So if you calculate U cross V and you calculate the length of it, then the length is the area of the parallelogram, or 2 times the area of the triangle. Or another way of saying is the area of the triangle is 1/2 the length of U cross V. And this first result is what in your book is theorem 3.53. That is a geometrical application of the cross product. So if U and V are 2 vectors with 3 components, then the norm of U cross V is the area of the triangle, parallelogram. That's first. With sides u and v, and 1/2 norm u cross v is the area of the triangle with sides u and v. Yeah. So, I mean, this is easy. Although the triangle is just 1/2 of the parallelogram. Okay, so this is actually really good in some sense. If you think about it, if I give you in space 2 vectors and ask you, oh, this parallelogram in space, what's the area? That's actually not so easy to calculate. It turns out it's pretty easy once you know about the cross product. No? Also, these are actually good formulas to know for 3-dimensional geometrical problems if you have to find areas of triangles and parallelograms, which include the special case of a rectangle. But then it's actually, yeah, but that's still also good for a rectangle. That's a special case of a parallelogram. Okay, now we do something else. And that's then the last thing, really. And we come back to something which I told you already before. It's about the geometrical meaning of the determinant. Okay, so the first thing what I like to do is I take 3 vectors, u, v, and w, and calculate the dot product between u and the cross product of v and w, and think about what is this. First, algebraic, then geometrically, and then we have another formula which comes out of the cross product, but we have actually an alternative way of calculating it. Okay, so first thing is we do the algebra. So we have 3 vectors, u, v, and w again, in the coordinate system with 3 components. That's the only way where we have. And also I will assume u has components u1, u2, u3, v has components v1, v2, v3, w has components w1, w2, w3. So that's what's happening in the following. And now we do first some algebra, and we are thinking, okay, if I calculate this, is there another way of calculating this? Does it really mean I have to calculate the cross product first? Once I have the cross product, I multiply dot product with u. Okay, so we write down first essentially our helper to how did we remember what v cross w is, or we write it as a determinant, no? So we write it as a determinant where this is only symbolically because it doesn't make sense to have vectors up here, but it helps. Then we have v1, v2, v3, w1, w2, w3. Okay, so this is how we can think about it. And now we have to, in order to calculate the determinant, I have to expand this determinant with respect to the first row. So we have u dot, and maybe I can make this a little bit shorter by writing this already out here. So this is u1, u2, u3 dot. And now I expand with respect to the first row, keeping in mind this. So now make a big parenthesis. So we have E1. Remember, this is 1, 0, 0. I don't like to write it now, but it's E1 times determinant of V2, V3, W2, W3 minus E2 times determinant of V1, W1, V3, W3 plus E3 times the determinant of V1, V2, W1, W2. So again, this is our goal. In the moment, we don't really know why we would calculate this, but we assume that's what we like to get. And this here is no longer symbolically. This really makes sense. No? So that means this number goes in the first component, this number with a minus goes in the second component, and this number goes into the third component. So how did we learn now that we do a dot product? So the U1 is multiplied by the first component, which is this. So it turns out this is U1 times determinant of V2, V3, V2, V3. Then U2 is multiplied with the second component, which is this. And we don't forget about the minus. So it's minus U2 determinant of V1, V3, W1, W3. And then U3 is multiplied with the third component, which is this entry, plus U3 determinant of V1, V2, W1, W2. Okay, but now you say, oh, what does this mean? We take this determinant, so from here and here, and multiply by a number U1. So that is the same as if there would be U1 here. Then we take, if there would be U2 here with a minus, we would take this determinant. And if there would be U3 up here, we would multiply by this determinant. So it turns out, once you see this, I'll say, oh, actually, that's the same as this one. Okay, so it turns out by purely algebra, we see if you have to do this, one vector dot product with another cross product, in order to do this, you don't have to calculate the cross product. All you need to do is calculate the determinant. That's purely algebra. So it turns out this is what's called a triple product also, dot product with a cross product, 3 vectors involved. Turns out this is just the old determinant. We are back in chapter 2. Okay, but now comes the critical question. So why in the world would we actually calculate this anyway? Okay, and now comes back to the geometry. What is this actually, this one here? So, and it turns out that again has actually a nice meaning, this one here, cross product with a dot product. And so now, okay, we have already a formula and you can calculate this one just by using everything you have learned in chapter 2, how to calculate determinant. For example, by Gauss or row column expansion, whatever you like, you can calculate this. Now the question is, what do we actually get if we do this? And so this actually finishes then today's lecture. So